Well, good morning. So what we did so far, last time, we did something very important, quite important. We showed that the response of an arbitrary LTI system could be calculated using the convolution process for any arbitrary input as long as you know its impulse response. So what we found out was that as long as you know the impulse response of a system, an LTI system, you know everything about it. That's even true about linear time-varying system as long as you have the catalog of responses. So you know all the responses impulse responses at all times. And one way to think about it was that impulse was a good thing to look at, although if you know its response to other things, you can also probably come up with some conclusions about it. Impulse was good because it demonstrated its natural behavior more openly or in a more raw fashion, if you will. So today what we'll do something, so we'll start talking about components that are going to have some dependence on time and behavior. In particular, we start talking about capacitors and inductors. We'll start looking at what they mean, how do we define a capacitor, what is the model for capacitor, how we analyze its behavior, and same thing with an inductor. Then we'll start looking at a couple of circuits, and we'll use those simple examples. We'll do a couple of simple examples with the capacitor to demonstrate something a little bit more important. And then we'll take that further and then look at, in terms of how the response can be broken into different components. So let's start with a capacitor. So if I ask you what is a capacitor, what would you say? So what is a capacitor?
Circuit element that stores charge.
Stores charge. So that's one way to think about it. Yes, it's a circuit element that stores charge. Fine, but it's accurate but not specific. I mean, you can make it even more specific. Any other thoughts? So the capacitor from a circuit's perspective is a right? So it's an element that has two terminals. And in the most general sense, a capacitor is an element whose charge depends on its voltage. So the most general capacitor is one whose charge is a function of its voltage. Now, this functionality may not be linear. Now, if I ask you what is a resistor, what would you say? Now you should know this, right? What is a resistor? Could you speak up? Current is a function of voltage, right? So a resistor, if I ask you, a resistor is one where current is a function of voltage, or you could say a voltage that's, conversely, you could say a voltage that's a function of current. It's probably easier to deal with. Now, a capacitor is something like that. So that's what we think about a capacitor in general. So in general, if you look at the Q versus V of a capacitor, it could be a nonlinear function. It could be even time varying. It could change with time and do different things. So that's the most general definition of a capacitor. Now, what if you so the very special case of that is a linear time invariant capacitor is CV. So the charge is proportional to the voltage, and the proportionality constant is called the capacitance, measured in units of farad, which would be coulombs per volt. Right? And we know, in practice, farad is a relatively large unit. That's why we usually deal with, in the lab, we usually with microfarads and nanofarads. And if you're making ICs, you're dealing with femtofarads and attofarads. And if you have really big capacitors on a chip, you're probably dealing with a picofarad, something like that. So that's basically what capacitance is. So now, what if the capacitance itself is, what if the capacitance can be time varying? If the capacitance can be time varying, so time varying capacitance. So what is time varying capacitance? Is Q is C of t V of t, or let's say Q of t. So for a time invariant capacitance, if the charge in the capacitance is Q, when you say stored charge, it is correct, but you have to think about it. It's not net charge. The net charge of a capacitance is what? 0, right? Because you get exactly the same charge here as there. And you remember from the circuit assumption and from Maxwell equations, you don't have really charge accumulation if you're dealing with a real circuit. So what it does, it basically says that there's some charge distribution that's of this nature. But so let's talk about that charge. And if that is the charge, what can you say about the current and its voltage? What is the relationship between its current and voltage of a capacitor? Of a, let's say, LTI capacitor. So what is current? Is rate of change of this charge, right? If you put current into it, if you put positive current into it, the charge will increase. If you put negative current into it, in other words, take charge out, it decreases. So the rate of change of that charge is the current, by definition. In which case you get, if C is an independent parameter from time, it's an LTI, from C dV dt, right? Which you can write also. You remember, I'm going to probably kind of sneak that Heaviside P operator in. So how would I write it in terms of the Heaviside operator? Cp of V. And over time, this will start, I may start even dropping the bracket. So I may write Cpv. But you have to be careful. This P is not a parameter. This is an operator. If I write it that way. What I mean is this. Yes?
Does it matter if it's uppercase or lowercase?
The P is usually shown with lowercase. Now, by the way, I'm using P to keep it consistent with the other material that you're looking at, the book and all those things. If I were to do this myself, if I were to write the book, I would not use lowercase p. I would use capital D, personally, because it's also kind of like more directly related to differentiation. But I'm just trying to keep it consistent for you guys. So it's a notation, right? I mean, but it's shown lowercase. This P is lowercase. So that's what that is. So that's the relationship between the current and voltage. So we can see the relationship between the current and the voltage and current, unlike a resistor, where the current was proportional to the voltage, or voltage was proportional to current. In a capacitor, the current is proportional to the derivative of the voltage. So this is something that you cannot capture with this. That's why you need a new element. No matter how nonlinear you make it or something like that, that dependency is not captured by a one-to-one relationship between current and voltages, right? Because for the same current, you may have very different voltages for a capacitor depending on the past history of what you've done to it. You agree? So I could basically have a current going in there, the voltage be 0 if there's no charge on it, or the voltage could be 5 volts if I've already charged it, and the same current going into it. So there's no one-to-one relationship between the current and voltage for a capacitor. That's why you need a different element. That's why we don't call it a new kind of resistor or a special kind of resistor. It's a different element in reality. So that's what the relationship between the current, if you know the voltage, you calculate the current this way. Now, how about if the other way around? If you know the current and you wanted to calculate the voltage, what would you do? Integrate, right? You do the inverse operation. So you basically what you say I divided by C times dt is dV, and then you integrate that. In other words, you basically say V of t, right, at any given time is going to be integral from negative infinity to t of 1 over c, which is constant. I'm taking it out of the integral in this case for an LTI capacitor, I of t prime dt prime, right? And in terms of a p operator, what does that look like? It's 1 over c, 1 over p of I, which I can also sometimes write this way. So I'm starting to abuse notation a little bit here, really. But it's OK. We'll see later on. So for now, I'll keep them this way. But don't be surprised by these. Because you will see that these eventually morph into something else. And that thing is very important. But it will take a few weeks to get there. So be ready for this eventually becoming something else, which is even more important. I can give you a little bit of I can tell you what it is going to be. And you can keep an eye. It's going to turn into a complex frequency. But we'll see that. It will evolve into it. For now, it's an operator. Think about it. It's something that takes a function of time, produces another function of time. Yes?
How do you do complex things and have I?
Oh, okay. That's why we use J. The question is, how do I use complex things with I and I? That's why in all the electrical engineering, square root of -1 is shown as J. So in all of your books and everything, you will see J. So as of this moment, as an electrical engineer, your I is transferred to a J. Translated to a J. All right. Any other questions on this? All right. So that's for linear LTI capacitor. But for example, what if you had a time varying capacitor, something like this? What would the current look like? So I of t would again be, by definition, dq dt, right? But now dq dt has two terms. The first term, which is similar to what you had, is c of t dv dt. But there's a second term, which comes from the different derivative of the product, which is v of t dc dt. So you can see that actually the rate of change of capacitance will also play a role in the current. So if you are given a time-varying capacitor, then you can have a second term in your current. And you will have a second term in your current, which you have to take into account. How do you make a time-varying capacitor? Come up with a simple example. Yes? Two parallel plates and start moving one of them back and forth, right? That's the simplest one you can make. Or I can make a parallel plate, I can put a dielectric in and push dielectric in and out, right? There are many different ways of doing that. There are other ways to make this, and you will see later on. For example, p-n junction diodes or MOS capacitors have a voltage dependence capacitance. So you can, by changing that capacitance, you can actually create a time-varying capacitor. Because where the charges actually are changes. So the effective plate spacing is changing. And you can use that and with this equation to do some interesting things, such as parametric amplification and parametric oscillation. But again, those are for later. Of course, so that's what happens in this case. And in the case of an LTI capacitor, we also know one more thing, which is an important, comes from basic physics. The energy stored in the capacitor is 1/2 CV squared, or 1/2 Q squared over C. So those are the basic properties of capacitors. And then beyond that, we can look at the equivalencies of capacitors. So let's say, for the sake of argument, you have capacitors in parallel. Again, we are going over some of the basic stuff. First, so let's say you have n capacitors, C1, C2, all the way to Cn, and they are in parallel, meaning they share the same terminal, two terminals. And then you're interested in knowing what is the equivalent capacitance, or how does this behave. So if this current is I, let's call this I1, this is going to be I2 all the way to In. And what are these these currents in terms of this voltage, let's say? So we know that I1 is C1 dV dt, right? By that definition. And I2, conversely, is this similar C2 dV dt, same voltage. And so on and so forth to In. So the total current, which is the sum of all the currents, is going to be sum of all these terms. But you can see that dV dt is common to all of them, right? So you can factor that out. So what you get is basically C1 dV dt plus C2 dV dt all the way to Cn dV dt. And that is equal to C1 plus C2 all the way to Cn dV dt. So this is some basic stuff you're aware of already. Just refreshing your memory on that. This is the current. So that looks like the current of a simple capacitor, C equivalent, dV dt, whose value is C1 plus C2 all the way to Cn. Which means that if you have n capacitors in parallel, the effective capacitance is the sum of the capacitors. Right? So in that sense, you could argue that capacitance behaves differently from a resistor, inverse. And if you put them in series, Again, this is nothing earth-shattering. Oops. I talk about resistor, I draw a resistor. So you have C1, C2, and Cn. So what is common now among these? What do they share? The current, right? So all of the currents are I. So this is V1, V2, and so on and so forth. So Vn here. So if their currents are shared, then I use the second equation, the integral form. So I say V1 is going to be 1 over C integral from negative infinity to t of I of t prime dt prime. Or for short, I basically can write it as 1 over C, 1 over P of I. Right? And so on and so forth for all of them. So if I write the total voltage V, which is the sum of all the voltages, it is going to be, so this is C1, C1. So it would be 1 over C1. I can write the integral, or I can write it this way. I'm going to write it this way. Of I all the way to 1 over Cn, 1 over P of I. And you can see that it's the same integral. This thing is the same integral, common to all those terms, so you can factor that integral out. Right? Whatever the value of this integral is. That is this, right? Which is a recurring term. I could have written it as integrals, but this is shorthand notation for doing that. And what you will see is that it's going to be 1 over C1 plus 1 over C2, 1 over to 1 over Cn times 1 over P I, which you can also, if you really write as 1 over C1 plus 1 over C2 integral from negative infinity to t of I of t prime dt prime. Which means that the C equivalent is, or more accurately, 1 over C equivalent, because this is now V, which is going to be what? V is 1 over C equivalent 1 over P of I, right? That equation. So more accurately, 1 over C equivalent is equal to 1 over C1 plus 1 over C2 all the way to 1 over Cn. So capacitors in series, the inverses of the capacitance in the series add, let's say. Let's put it this way. So basic properties of capacitors. Any questions? So the key takeaway from capacitor is that really, if I ask you what is the most fundamental definition of a capacitor, at least from the circuit standpoint, what is it? Yeah, it's a component whose charge depends on the current. I mean, on its voltage, sorry, I misspoke. Its charge depends on its voltage, sorry, yes. Yes, I misspoke, thank you. You know, it's good to have somebody correcting me here, otherwise I would say all sorts of things. Fact checkers. Good. All right. So we talked about resistors, we've talked about resistor before, and we talked about capacitors. Now there's another element that's very important in electrical circuits, which is the inductor. So what is an inductor? I mean, you've seen, I'm sure, the inductors in the context of physics. It's you know, a certain component. Sometimes you've seen it as coil, as implementations of that. But what is an inductor? What is, if you wanted to use these two analogies of resistor being a component whose current is a function of its voltage in general, and a capacitor is a component whose charge is a function of its voltage, what do you think an inductor would be? Think about it for a second. And yes? Something, so this, something that whose voltage depends on the change of current, which is correct, but it's not the most general definition. that is akin, what you said, is at the same level as this definition of capacitor. An LTI capacitor, that would be an LTI inductor. I am first looking for this level of definition for an inductor, whose what is a function of what. So inductors are usually what kind of, capacitors are electric devices, right? Electrostatic devices, if you will. Inductors are magnetic devices. So do you think, what parameter? And charge is a measure of electric field. Now, what is one of the measures of magnetic field? Flux, right? So inductor is a component whose flux depends on something, is a function of something. What is that something? Is magnetic flux. What do you think that thing is? This is a two-terminal component, right? So it has to be a function of one of those two parameters, the circuit parameters. Yes? Current, yes, exactly. So the most general definition of an inductor is a component whose magnetic flux is a function of its current. And through a very similar derivation, and we won't really belabor this point again, so you can go through all of those assumptions, approximation, all those things. If you have a time varying one, you will have two terms because it would be a product of two linear time varying one. And if you have an LTI one, then you have a flux that's proportional to the current. Proportionality constant is called inductance, and it's measured in units of Henry, which is also a rather large unit for the typical components you deal with. For typical components, probably not as large as a farad. Again, this is just completely rule of thumb, typical for the way we do things today. So you're dealing with, for example, on integrated circuits, you're dealing with nano and picohenries, while you're dealing with pico and femtofarads. So it's like about a factor of 1,000 kind of difference for what is typical. But again, typical is all in the eyes of the beholder, right? So all right, so if that is the flux is good and nice if you're dealing with physics, but if you're dealing with pure circuit properties, what I really care about is the voltage, right? What is the voltage as a function of flux? If you know the magnetic flux, there's a relationship between the magnetic flux and the voltage, right? Where the voltage is basically the derivative of the magnetic flux with respect to time, and therefore it would become L di dt. Correct? Good? Excuse me. All right. So, and as such, you can write it as, if you wanted to use the notation. How do we do that? The heavy side, L P of I, or LPI, you can shorten. And conversely, again, if you want to calculate the current, it would be 1 over L integral from negative infinity to t of v of t prime dt prime, which you can basically write as 1 over L 1 over P of I, V, which you can also write as 1 over LP if I go loose and fast with the notation. Okay? So those are basic components, really elementary components. Now, if you think about it at the end of the day, these things basically take it one level higher, right? Resistor current dependent on its voltage, right? Now, if you look at the capacitor current, it depends on the derivative of the voltage. If you look at the inductor current, it depends on the integral of the voltage. So you have one component whose current depends on the voltage, one component whose current depends on the derivative, and one component whose current depends on the integral, levels up and down. And you may come back and think about it and say, what if I have a component whose current depends on the second derivative, or its voltage, or second derivative of the voltage? Or a component whose current depends on the second integral of the voltage? Can you define such components? And you can. And you will see that they're not as general as these things, actually. In fact, you can generate components that behave that way using active circuits and these. Right? Because once you have one derivative, for example, you can try to think about it this way. If I have a derivative, something that takes a derivative, and if I convert that current, let's say this current back to a voltage, what is the easiest way to convert a current back to a voltage? Resistor. A resistor. Which is exactly right. So the resistor is one way of doing it. Now, in practice, we won't really use a resistor because of unilaterality and bilaterality we talked about. So if you start just connecting a resistor to it, then that would affect things backward too. So you need some sort of buffering. You need an amplifier or something like that, separating them. But if you do that, then you have another voltage, and then you can put another capacitor and get the second integral, or put an inductor and get second derivative. In fact, you can actually even emulate an inductor by using two capacitors and what we call and two conductances. So you can actually even emulate, it's called a gyrator and all things like that. So we'll, again, won't cover those, you will see those later. So, but you can see that now you have a good set of Lego pieces to play with. Now you have expanded them, right? Because if you think about them, say, okay, I have this thing that does this, and if I want to put them together, I can play games, build things. Any questions? No? All right. So let's start with a very simple example. Now, this simple example is useful first because it shows you how to do these things if you have any questions or if you're rusty on them. But it's more important because it will allow you to think about a different kind of decomposition of the response. So we are trying to use this first to do the example, but second also to understand how these responses behave. So think about something simple. Think about let's say a voltage source. Let's say it's a fixed voltage source for now, Vs. And then let's say there's a switch here and a resistor connected to a capacitor. You can define this as ground if you prefer. R and capacitor C. And this is the switch. So let's say the switch turns on at t equals 0. So this notation means that at t equals 0, it's going in this direction, which means that it turns on. It closes. And let's say the capacitor has some initial voltage V0. I think that's what I assume. Yeah. So let's say it has some initial condition, initial voltage on it. That's V0. Now, you have something like this, and then the switch closes at time t equals 0. My question to you is, what is the voltage across this capacitor? Let's say that you could call this the output voltage or whatever you want. What is this voltage over time, at all times? How do you find that? So there are different ways to do it. And we'll do it a certain way now, and then we'll see better ways of doing it later on, or easier or more straightforward or more generalizable ways of doing things as we go. So the basic way of doing it, the phys 1 or phys 2 way of doing it, right, essentially is to say, look, there are a couple of things I need to know. Once the switch is closed, the first thing I need to find out is that is the closing of the switch going to instantaneously change something? Some of the initial conditions. Is it going to, for example, change the capacitor charge? Do you think it can, when I close the switch, the charge of the capacitance can change instantaneously? Okay, you're saying no. But why? What does it take to change the voltage of a capacitor? The voltage of a capacitor is 1 over c integral from negative infinity to t of I t prime dt prime. So if I want to get an instantaneous change in this voltage, what needs to happen to the current? Say again? Needs to flow over an amount of time. But that doesn't mean instantaneous, right?
A non-zero amount of time.
Okay. Yes, in the back?
You have to have like an impulse of current like
Right, you have to have infinite current. Think about it. This is an integration process, right? So the question I'm asking is that if it is going to happen over an infinitesimal time, how much current do you need for an instantaneous change? You need infinite current because it's being integrated, right? If I have a finite current, right, the integral of this is going to be something like this. The integral of this is going like that, and then starts changing slope like that. The only way you can have a jump in the integral is that this thing goes to infinity, something like an impulse. Or something like an ideal voltage source being attached to it, something that can provide infinite current. Now, why is it that this cannot provide infinite current to the capacitor? What is the thing that limits the current? The resistor, exactly. So the resistor doesn't, if it's non-zero, it basically limits the current. So you can't have instantaneous current of infinity. Because if you have an ideal voltage source and put it next to a capacitor, or have two capacitors that are charged to different values and attach them, then you can have infinite current, right? But with the resistor, it won't happen. So that's for that. So we know that there's not going to be an instantaneous change in the voltage. And what that means, the way we write that, is that we say V of 0 minus is equal to the V of 0 plus. Which is going to be equal to what? Or the other way, I should have actually written it this way because it makes more sense when you say it. So V of 0 plus, after closing of the switch, is the same as the V of 0 minus. This is not always true. This is true in this case, which is equal to V0, the initial voltage of the capacitor, right? So that's what the voltage is. So now I know that at that transition time, nothing extraordinary happens in this example. And as I said, this is not always the case. So, let me redo this. So it was the voltage, V of t, was at V0 before I closed the switch, and then it didn't change. So at 0 minus and 0 plus, it's still the same. So now from 0 plus, I have a circuit that I can solve, right? Nothing is changing in that for now. So I have so how can I solve this circuit? One of the things I could do, for example, I can write KCL on this node. To write KCL on this node, when the switch is closed, I have to say the sum of these two currents is 0. Right? So what is the current through the capacitor in terms of the voltages? So this current, what is this current? I'm doing very basic nodal analysis, essentially. What is this current? In terms of this voltage? It's a capacitor. Right? Look at the definition of a capacitor. So what is it? Yes. So that current is, so I'm saying that this current, let's call this IC plus I1 are 0. So IC, I1 plus IC is 0. So I'm writing that. So IC is C dV dt because of the capacitor, by definition, if this is a capacitor. Right? Plus this current. What is this current in terms of V of t? What is it? V of t minus Vs divided by R. Right? The voltage across this resistor. When the switch is, now the switch is closed. Equals 0. So I could write this as C, or I can divide both sides by C. So I can write it as dV dt plus 1 over RC V equals Vs over RC for t greater than 0. So that's the equation that describes this voltage, the differential equation, which is an equation of the form y prime plus 1 over tau y equals some x. Right? And in this case, we are defining RC as tau. So tau equals RC. Now this is an important parameter. It's called a time constant, as you will see in a circuit. So it has units of time, it has units of second, and it defines a property of the circuit. So time constant is a very important one. Now, if you take that, so this equation, this differential equation, how do we solve this differential equation? Well, if you wanted to solve just this differential equation, right? You wanted to suggest something? Oh, sorry, I thought. Yeah, that's all right. So, okay. So how do we go about solving this differential equation? Well, there are different ways to solve it. One way, in this case, you can actually do separation of variables, right? So what you can do, I can move this whole thing to the other side. After I've divided by r, so I get dv dt equals 1 over rc vs minus v of t, right? And then I can take this and move it down here and take this differential dt to the other side. So the left side would be a function of v. Again, this is a very special way of solving this. This is a very rudimentary way of solving it, let's put it this way. We'll come up with much more general ways of solving these things soon. But again, it becomes dt over rc. Right? I've just taken this term, put it here, taken this, put it here. And then now you can integrate it, because this side is a function of v, this side, so I don't even need to write it this way. This side is a function of t. So I can integrate this and integrate this. I can integrate it from 0 plus to t. I can integrate it from v of 0 plus to v of t. They have to match, right? The left and right limits have to match on an integration of this sort. So what is the right-hand side? The right-hand side is easy, right? What is the integral from 0 plus to t? T over rc. Or you could write it also as t over tau, because we define tau as the time constant. And how about the left-hand side? What is that integral? Well, what is the integral, the indefinite integral of dv over vs, did you call vs? Yeah, vs minus v0. Natural log of, right. Well, there's a minus sign here, right? So I could actually take, why don't we do this? Why don't I just make this v minus vs and put the minus sign on the other side? It's actually better. Okay? We're good with that? So we got negative t over tau, and here we got this. So then becomes a natural log, because this is u, you can define this as u, and du and dv are the same. Otherwise, you have to deal with another minus sign that would pop up. That doesn't matter. It would be the same answer. So it's natural log. So what we have is a natural log of v of t minus vs minus, right, the natural log of v of 0 plus. But v of 0 plus is v0, right? It's the initial condition. Minus vs equals negative t over tau. So where do we go with that? What is the natural log minus natural log? What's the difference of two natural logs? Is the ratio of the arguments. Natural log of the ratio of the arguments, right? So this is basically natural log of v of t minus vs divided by v0 minus vs. Which I can basically, again, take one further step. I can do exponential of both sides. So I get v of t minus vs equals v0 minus vs times e to the t over tau, right? And I can move this to the other side and get some answer. V of t equals vs plus v0 minus vs e to the negative t over tau. So that's the solution. So if I were to let's do a clean one now that we know the answer. So the response to this system, response of, I guess, this system, which is an LTI system, So I'm just redrawing it. This is Vs, initial condition is V0. This is V of t. Oh. And then that becomes, so we know V of t from the solution that we just derived is Vs plus V0 minus Vs. Okay, so let me just do it slightly different. So it is Vs plus V0 minus Vs e to the negative t over tau. This is for t greater than 0. And what is it for t smaller than 0? V0. And you can see, actually, so what we know is that it shouldn't change from t equals negative, 0 negative to 0 positive, right? 0 minus to 0 plus. Does it? Let's see. At t is negative 0 is V0, as t equals 0 minus. And at 0 plus, let's look at this. If I set t to 0, what happens? What is the exponential? What's e to the power of 0? 1. So Vs cancels negative Vs, and then I'm left with V0. So it's continuous in that sense. So if I plot this versus time, it looks like this. So it starts at V0, so this is V0, and asymptotically reaches Vs. If you look at it, why does it asymptotically reach Vs? See what happens if t becomes very large. Right? What is e to the negative t over tau if t goes to infinity? 0, because it's a negative, right? So it's an exponential that's e to the negative minus large number, negative of a large number. So it's 0. So this becomes 0. So you'll get to Vs. So you have this kind of exponential, by the way. From time to time, by the way, I see something on people's problem sets or exams and things of that sort. Be careful. This exponentials of the negative sides, with the negative argument, behave this way or this way. They don't behave this way or that way. So I see people showing sometimes responses that look like this. You laugh now. I hope it's as trivial to you as it's later on too. Right? So again, if you want to think about it, say, well, yeah, sure, it's a negative exponential, so it just has to go like this. And what happens is that they remember it's an exponential and say, well, but exponentials go like this. Well, those are exponentials with positive exponents. So keep that in mind. Anyway, so this is what it is, right? So I can actually take a look at this response and say, well, okay, this is an interesting response, and I can do something useful with it. But I can also write it in terms of two responses. So I'll write it as something, as a way of introducing you to a more important concept here. So I'm going to write it as, what's the best way of doing this? Okay. V of f of t, and V sub n of t. And I'll tell you what I mean by each one. So Vf of t, for V of f of t, I write 0, t for t smaller than 0, and Vs times 1 minus e to the negative t over tau for t greater than 0. And for Vn, I write this. V0 for t smaller than 0, and V0 e to the negative t over tau. And I can write the overall response. So the purple response is the sum of the blue response and the red response. You agree, first of all, mathematically this is correct, right? If I have these two things and I add them, I get this. But this particular decomposition is actually pretty meaningful. F stands for forced, and N stands for natural. So what do we mean by forced response and natural response? So this is one of the decompositions. There are other decompositions that we can make for a response. So the natural response is what this circuit does if there was no real output perturbation applied to it, or if there was no input to it. It's what it does naturally, without any outside influence. To use people's analogy, right? Humans are like this. I mean, there are things you naturally would like to do. There are things that you naturally gravitate to. Each person is different. They naturally would like to do this, different things. They have talent, interest, etc. in it. So this is what the circuit would have done without this Vs. If this Vs were 0, think about what happens if this Vs were 0. Basically, it was a short circuit, right? Before the switch was open, before the switch was closed, when the switch was open, you had some initial condition V0 on this, right? When you close the circuit, you're essentially discharging the capacitor. You're putting a resistor in parallel with it. And it would decay exponentially, right? So this response looks like this. So this is V0, and then it exponentially just dies. Right? Make sense? This is what it does naturally. Now, this is what's forced upon it by the outside world. Your upbringing, your friends, your teachers, the TV, etc., all of that stuff around you, right? This is what that's turning you into. Not necessarily a bad thing. You could argue that if we were just left to pure or natural responses, we would be still cavemen. But, or worse. But anyway, nonetheless, so that's what the influence of the outside world is on you. So this forced response, you see the forced response, there's no forced response, 0. Because there is no input before t equals 0, right? It's only after t equals 0 that there's an input applied to you, to the circuit. There's some outside stimuli, or stimulus in this case. Now, and what it is that it basically jumps up to 1 at t, I'm sorry, it doesn't jump up. So so what is it at t equals 0? At t equals 0, it's still 0, right? So it's continuous. And then what happens beyond that is that it gradually, exponentially goes up to a value of Vs. Both of them are happening. Now, these exponentials are not well defined, and neither is this one, unless I write the time constant. So tau equals RC. Because there are many, many different exponentials that can be defined by these asymptotes, right? You agree, right? I can draw a lot of other exponentials that go from V0 to Vs. I can show you. I can show to make this. I can make this. I can make all sorts of other things. So without telling me what the time constant is, or without me telling you what the time constant is, this is incomplete. So now it's complete. Now it's good. But going back to the forced response and natural response, what you see is that there are really two things to this. So even if you think about it on a day-to-day basis, there's a natural response and the forced response. The forced response, is essentially your reaction to the things that are imposed on you. You have your problem sets. You have things of that sort, right? You have to do it's forced response. Anyway, so this decomposition is important because they can be calculated differently for a circuit. And they tell you something different about the complete response, which is the sum of those. Now, there's an alternative decomposition. So I'm going to try to put it on this one as well. Let's see. Okay. My color combination is not going to work perfectly, but that's okay. So there's another way to decompose this V of t, right? So let's write it this way. V of t, let's write the V of t as two different responses. So let's say I have a blue response, which I will call Vt sub t of t, or Tr of t. And then I will have an orange or yellow response, in this case orange, which I call Vs sub Ss. And there's a reason for these things. But before we talk about these, I don't want to use yellow, and I don't have a yellow anyway, but to make the green out of those two. But it's the closest surrogate. So if I write it this way, and if I say VSS is really this is VSS. Or, yeah, t smaller than, or let's just think about t greater than 0. Let's just focus on that for now. Let's say VSS is Vs. And VTR is V0 minus Vs e to the minus t over tau, also for t greater than 0. Right? This is another breakdown. This is another decomposition, right? VTR of t plus VSS of t. So what are the characteristics of these two responses? Say again? Okay, yeah, sure. It's time dependence, right? That's good. So this one is time independent. Actually, SS stands for steady state. Okay? And TR stands for transient. So this is the transient response and the steady state. Now, it's transient and steady state don't necessarily mean time dependence, by the way, or time independent. In this example, they are. You can have a steady state solution that's time dependent. For example, if I apply sinusoid to something, a constant sinusoid to a circuit, right? Let's say the circuit is off, and I start applying a sinusoidal function to it. Initially, it will do some transient thing, right? It will react to it. It will go through some transient. But after a while, those things will decay usually, I mean, depending on what kind of circuit you have. And you're left with a response that's steady state, right? So you have, each one of us has this steady state response in response to day and night, for example, right? We wake up, we sleep, wake up. We may be in different phases, but still, we wake up and sleep, right? More or less with the day and night cycle. So that's a steady state response. But on top of that, we have transient responses. Sometimes the weekend is maybe different from the weekday. Exam time may be different from different times. You know, when the homework is due, this cycle is perturbed by transient, right? So this is the transient response, and this is the steady state response. So that's another decomposition. That's also important to think about. Now, all of these things said, if you have a first-order differential equation, if you have a first-order circuit, there's an easy way and quite useful way of finding the solution. So this is something we know that a first-order system's response, the first-order differential equation's response or solution, is of the form of an exponential, right? So if you have an exponential, e to the negative t over tau, and these have like some sort of time constants associated with them. So we are trying to define the most general form for some v of t or I of t, some solution to this problem. When something happens at t equals 0. Now, what if something doesn't happen at t equals 0, it happens some other time? You can actually shift your time base to that point and assume that t equals 0, and then take it from there. Okay? So if you're studying, so we are going to construct the answer. We are trying to construct it, right? So you know that the response of the system is that it will go from some initial value, let's say the initial value, let's call it v of 0 plus, exponentially to some final value, v of infinity, right? So we want to construct a function that goes from some initial value to a final value, And you don't even worry about stuff that happens at negative time for now. Right? That's before Big Bang. So now, you go from some initial value, let's say V0 plus, to some final value. You're trying to construct with some time constant tau. You're trying to construct a waveform, a function that does this. How do we do that? Well, what is the value of this function at t equals 0? Right? At t equals 0, what is the value? What is this at t equals 0? 1. What is it at t at large t's? 0. So I have a function that starts from goes from 1 to 0. What do I want the value to be at t equals 0? V of 0 plus, right? And what do I want it to be at infinity? This function, V infinity. So at V infinity, this guy is 0, right? So whatever is multiplied by it, it shouldn't have any effect. So what I can put down is that I can write V of infinity here. Plus, so as long as V of infinity is not multiplied by e to the negative t or minus tau, this would produce V of infinity at at large t going to infinity. So what I need to do is to make the rest of it such that the rest of it is stuff that gets multiplied by the e to the negative t over tau. And I need to make this such that at t equals at 0 t, this produces V of 0 plus. What should I make this so at t equals 0, this whole function becomes V of 0 plus? V of 0 plus minus V of infinity, right? Did I make these lower cases? Okay, so let's make them lowercase. Do you agree? Because at 0, this is 1. So this guy cancels that. You're left with this. And at infinity, this is 0. So you're left with that. And all you need to make this complete is this. Because it's only dealing with things after t equals 0. Now, this is actually quite useful and important. I think this is the second thing I've boxed. The first one was the convolution. I don't usually box a whole bunch of things. But this is very, very useful. I wouldn't say it's really as important as the other one, but it's definitely very, very useful in the stuff you will be dealing with. Yes? Okay, so think about it. What's the transient? What's the steady state in this case? This is the transient. This is the steady state. How about forced and natural? This is the natural. These two, this and that, times that, are the forced. So there are two different decompositions. Okay? Any questions? And of course, if time is not equal to 0, we can always shift the time base and make it 0. So let's do a quick example with this. Let's do a quick example and see where it takes us. So I have an example here. So let's say you have and you will be doing more of similar kinds of example going forward. So let's say this is Vs equals 12 volts. Let's say there's a resistor of 4 ohms here. There's a capacitor of 1/4 of farad. Again, this is not good engineering notation. This is mathematical notation. If you're an engineer and write a quarter like that, really good engineers should not be very happy with you. Unless they are not, they don't know what they're doing either. But again, for this mathematical problem, we're writing it this way. and this is Is of 4 amps. And this switch switches from this side to that side at t equals 0. And the question is, what is the voltage across this capacitor? And the initial voltage, V0, at time t equals 0, well, we need to find that. Okay. All right. So this is what we are trying to solve. So at t before, at negative t's, this switch has been on this side, right? So the first thing, and what we are trying to do is to find v as a function of t. So how do we do that? When this switch is closed on this side, so let's say this switch has been close to the left for a long time. What is the voltage across that capacitor? If that switch has been on for a long time? 12 volts, right? I mean, this voltage across here, because if it has been on, so it must have reached steady state, and in steady state, basically this voltage the current should be 0, this current. So this voltage should be the same as that. There's no current flowing, there's no voltage drop across the resistor. This voltage should be the same. So initially you start off at 12 volts. Now at t equals 0, you switch to this side. Okay? What happens? So think about it. First thing you have to find out is that, do you have a means of delivering infinite current? Because you want to see if there would be an instantaneous change in the voltage or not. So how would that happen? If I had a voltage source here, let's say, right here across. Instead of the current source, I had a voltage source of 8 volts. This would instantaneously jump to 8 volts, right? If it's an ideal voltage source. Because the ideal voltage source is capable of providing infinite current. But we don't have a means of delivering infinite current. Neither the resistor nor that current source of 4 amps can provide infinite current. So what's going to happen? So in that sense, where is it going to go? So there's not going to be a sudden jump. So 0 minus and 0 plus are the same. So you're going to stay at 12 volts. So what's going to happen afterwards once this switch is closed? So we are starting at 12 volts, and we want to see where we are going to end up. So what are we going to use? That expression that we just developed. Okay? So what is V? So that expression said this voltage V of t is going to be V infinity plus V0 plus minus V infinity times e to the negative t over tau u of t. And don't forget these u's of t's, because you will see they are important. So what is V infinity? Or what is V of 0 plus? This is 12 volts, right? We already determined that. So you need to find V infinity. What is V infinity? How do we find V infinity? Let me ask you this question. In steady state at V infinity, what is the current through the capacitor? 0, right? So that means that all of that current goes through what? Which means that voltage across the capacitor should be what? 8 volts, right? 4 amps going through 2 ohms, right? So V infinity is going to be 8 volts. And now what is the time constant? That's equally important, if not even more important. So you need to know what the time constant is. What is the time constant? The time constant in general, the way you determine it for a capacitor, is that you look at the capacitor and see what is the resistance it sees when you null all the independent sources. So what resistance does this capacitor see if you null from its terminals, if you null all the independent sources? 2 ohms, right? So it is tau is going to be whatever, 1/4 of a farad times 2 ohms. So 1/4 of farad times 2 ohms, it's going to be half a second. So this becomes negative 2 times t, u of t. which you can write as 4 volts essentially here. So it is going to go from what to what? It's going to go from 12 to 8. So I say this is 8 volts with a time constant of what? Half a second. Right? So it's going to, how is it going to look like? Is it going to, show me with your hands. Right, like this, right? So it's going to start dropping. So this is the asymptote. It's going to go keep dropping, right? So now let's say at some point in time, at, let's say, I don't know, t equals natural log of natural log of 2 seconds. I flip the switch back. Right? I can annoy you on your problem sets by keep doing this. And you will see some of this. But, all right, so let's say I bring it back and switch it back at this time. So what is going to happen? E to the negative, what is then e to the negative 2 natural log of 2 is going to be? What is it? It's not a very useful thing, actually. Anyway, so let's just pick some numbers. So let's say t equals, I don't know, 4 seconds. Right? At t equals 4 seconds, what do I need to do? At t equals 4 seconds, I need to calculate e to the negative 2 divided by 4, so e to the negative 1/2. So I will plug that in. This produces a number, right? If I set t to 4, it produces e to the negative 1/2 times 4 plus 8. So it becomes 8 plus 4 e to the negative 1/2, whatever that is. So that's the voltage at that point in time, that V of 4. So at some volt level, you reached some level. So let's say this is that level. Now, what happens is that beyond this point, none of this matters. Because now you've pushed the switch back to this side. So now you're starting from a new initial value, which is this value. Right? This is in that expression your V of 0. Because now you can shift your time base here, shifting everything as t minus this number. You can call it t1. And then you will go to a different asymptote. So what will be the V infinity now?
Why do you divide by 4 to get minus 1/2?
I'm sorry, what did I do?
Minus 2t, so it'd be minus 2 times 4.
You're right, e to the negative 8, right? I made a mistake. That's why I did. Thank you. So this is whatever that value is, e to the negative 8, which is pretty close to 4, actually, if you think about it. Right? It's negative to pretty close to 8, because e to the negative 8 is pretty small. If I pick a number like that, then it has almost reached 8 volts, but it's a little bit over 8 volts. But from that point on, you start with a new one. So now you're going to go towards a new asymptote. What's the final value when the switch back this way? What is the value it's going to go towards? 12. So it's going to go. And now, what is the time constant? Is it the same time constant? No. So this is tau 1. So this is tau 1, which is 1/2 a second. But now, when I switch to this side, I have a tau 2, which is 1 second. So it's slower time constant. So it will go towards that asymptote, but with a slower time constant. So it will go at a slower rate. Now, if I at some other future time I switch it back, what do? Again, I use that new expression that I would get to calculate what the value is and use that as the new initial value and calculate again the asymptote and go towards that. So I can keep doing this in different ways and get the answer. All right, any questions? All right. If not, let's take a quick break, and then when we come back, we'll continue.